This is a video discussing molecule polarity. And as we can see here, the word polarity has the word pole in it. And so when we think of poles, a lot of times we think of a magnet with opposite ends, north and a south pole, and our planet with also poles, north and south poles as well. And so that's what we're going to be looking at in this video, that molecules, this one seen here, water, happens to have overall a polarity to it, opposite poles. And so you can kind of see up here, we've got a slightly negative and a slightly positive end. This end of water is slightly positive, this end of water is slightly negative, annotated by those little symbols, Greek symbols seen here slightly, right? So something that I want to make sure that you don't mistake, and that is we're actually talking about the entire molecule's polarity, which is why in this picture I had the entire molecule circled here, and not just a bond polarity. So that's a bond and that's a bond. So molecule polarity is this video versus a previous thing we learned, which was bond polarity. A lot of students make the mistake and think when we ask about a molecule's polarity, we're asking only about its bond, and that is not true. So this is our new topic for today. This we covered previously in another video called electronegativity. So that might be a good video to go watch before you watch this if you forgot what bond polarity is. Why do we have to know bond polarity? Well, bond polarity is part of, it's going to be referenced, molecule polarity. So it's part of it. Okay, I'm going to do a really quick review, but again, you probably want to watch that video if this is not ringing a bell. So electronegativity, abbreviated with EN here, is an atom's ability to attract electrons to itself when in a bond. So here we got hydrogen and chlorine, just to make this simple. And each of these have their own electronegativity values. And so if we take a look at that, we can see here that hydrogen has an electronegativity value of 2.1. I looked it up on an electronegativity scale or an electronegativity chart. You were given one that looks like the periodic table, and inside each box was every element's periodic or electronegativity value. So I looked that up on a reference sheet. And then chlorine has an electronegativity value of 3.0. And if you remember, the math we did was super simple. We just subtracted them. Then we were introduced to the scale that then helped us classify this bond right here. Is it a nonpolar bond? Is it a polar bond? Or is it an ionic bond? Nonpolar, polar, or ionic? Obviously, this is going to be a polar covalent bond because when I subtract the difference, it ends up being 0.9. So I like to call electronegativity like a pulling value, how well an atom can pull electrons closer to itself. Okay, so that's a little bit of a review. The last thing I want to review is this arrow seen up on top here, and it's kind of a fancier arrow, and it's called a dipole moment. And you could see here that the arrow head points towards the more negative side of the molecule, so that's the higher electronegativity value. And remember, this bond is made up of those electrons, and chlorine pulls those electrons slightly closer to itself. Not fully, because if it did, that would be a complete transfer, and that's ionic. This is still covalent. And then you could see here the positive tail is the side that's just slightly more positive. Well, what would make you slightly more positive? Your electrons that you're sharing are not as close to you, seen in hydrogen, they're closer to chlorine. Okay, that's review. You're gonna have to know a little bit of that for today's molecule polarity. So for molecule polarity, these are the things we're gonna consider in this video. Bond polarity, which we just reviewed, and something called symmetry. Symmetry is going to be taking into consideration what your outside atoms look like, right? The atoms bonded to the center of the Lewis dot structure, and the shape of your molecule. And in particular, we're going to be looking at lone pairs. So this is what lies ahead. So let's first start with, what does this word symmetry mean? You probably have heard about it in math class. Symmetry is, for our purposes, the easiest way to think about it is when your outside atoms, right, the atoms that are surrounding the center atom, are evenly distributed around that central atom. Evenly distributed. So let's take a look at some examples now, and we're going to see if your molecule is polar. And if your molecule is not polar, then it's considered to be nonpolar. So let's bring back our example of water seen here, okay? So I'm going to now calculate for two things, and that is first I'm going to calculate the bond polarity. So let's go ahead and do that. That's the bond. But remember, that's not the only thing I consider when I do a molecule polarity. That's just the first thing. So here's water just drawn a little bit more simply. And I went ahead and I looked up the values for oxygen. And so oxygen's electronegativity is 3.5 and hydrogen's is 2.1. So clearly oxygen is more electronegative. So the electrons in this bond are pulled closer to oxygen. Now I'm going to go ahead and bring back that idea of the dipole moment. So let's draw those in. Remember, the tail has the positive end and it points towards the more electronegative end. So there's my dipole moment, and the same thing happens on the right-hand side. Let me make that arrow a little bit better. Okay. So now I notice that my two dipole moments are pointing towards the oxygen. And if you remember, you can even put in the lone pairs. Oxygen does have lone pairs on its center. So I went ahead and calculated this, or I can actually just look at this 3.5 and 2.1, and when I subtract them, there's going to be a substantial difference, which means then these bonds here are polar covalent. So I'm going to write polar covalent, polar covalent. Okay, so I have polar covalent bonds. That's one thing to consider, right? So here we are. The next thing I want to consider is there symmetry? So first of all, my bonds are polar, which is a good indication that I might be a polar molecule, but it's not the only thing I consider. So now I have to see if my molecule is symmetrical or opposite, which is asymmetrical. I automatically notice that the atoms that surround the center, remember we talked about symmetry, the atoms, and I notice that they're not evenly distributed. They're over here on the bottom versus some protruding out at the top here, right? And so those outside atoms are not evenly distributed around the center. So if you're not evenly distributed, then you're not symmetrical. You're asymmetrical. So right now I have an asymmetrical molecule. Well, that makes sense because let me bring back that original picture we had. We said that this side of water is slightly negative, and we know that because the electrons are being pulled up in that direction. And this side of water is slightly positive, right? And we know that because these hydrogens have a lesser electronegativity value. So the combination of having a polar covalent bond, meaning pulling of electrons are happening, and the fact that this is not symmetrical means that the charges are not evenly distributed there. So I have charge up here and a charge down here, means that this molecule is polar. So now let's go back to some of these kind of funny analogy pictures. Remember, polarity means you have poles, opposite poles. And so I look here and I say, yeah, that's what's happening here in our molecule. We have a positive pole here and a negative pole there. And these poles, right, we took into consideration two things. So let's go back, well, kind of three things. Bond polarity, symmetry, which these two questions were looked at. So now we've noticed some sort of, commonality, and that is in a polar molecule, we need the shape, the overall shape here to be asymmetrical, and it helps if the bond is a polar bond. So polar bonds and an asymmetrical shape for a polar molecule. Okay, let's go on to another example, and let's now look at CO2. I went ahead and found the electronegativity values, and clearly there is definitely an electronegativity difference between these. And so when I classify it, the bond is polar covalent. Okay, remember, first thing, bond polarity. Now I have to talk about symmetry. Remember, a second ago we said if your bond is polar covalent and you're asymmetrical, then you have poles of positive and negatives on your overall molecule. Let's see what's happening here. So let's go ahead and draw in our dipole moment. Remember, from the center is where I start, and I notice that that's the more electronegative end, and that's the more electronegative end. So I'm going to first draw my dipole moment for this bond, and my arrow points to the more electronegative, leaving the carbon slightly more positive. And then I'm going to do the same thing here, and since it's the same exact atom, I'm going to draw the magnitude of the arrow to be the same. Well, what do I notice? When I line up these two dipoles, so let me line them up on top of each other, one goes this way and the other one completely goes in the opposite direction, equal and opposite, they cancel out. So what I have here is a perfectly symmetrical shape, right? So if in this instance, because my outside atoms are distributed evenly around the center, right? Evenly distributed, one on this side, one on this side. They're exactly the same, that's important, and they're pulling in equal and opposite directions and they cancel out, then this is symmetrical, which means then there's no net pull, right? It's almost as if you were playing tug of war with yourself and you're pulling on this side and exactly you, the same person, is pulling on this side. Well, is the knot going to go anywhere? No. So there is no polarity to this molecule. So this molecule is non-polar. So now we put together something about nonpolar molecules. They have to be symmetrical, but their bond doesn't necessarily have to be nonpolar. So it could be polar or it could be nonpolar. So the bond can go either way on this one, okay? All right, let's look at our last example here. And again, I've picked a linear looking molecule and I put carbon in the middle. But in this time I actually put oxygen on one side but sulfur on the other. So I got their electronegativity values, and I noticed that this is such a small electronegativity difference right here. And so that difference is probably going to give me a nonpolar bond, whereas this side is a polar bond, polar covalent. So look at that, two different types of bonds. So now I have to go on to the next question, and that is talking about symmetry. So I'm going to put my dipole moments in place, and I notice this one significantly pulls more on this side. Oxygen definitely has a greater electronegativity value, whereas the difference here is so small that I'm going to draw that magnitude by showing you by using a really small arrow. Now if I go ahead and line up those two dipole moments, I notice they don't cancel out. Can I show you that? So because they don't cancel out, then this is asymmetrical, right? There's definitely more pulling going on here. So there's a pole over here, and this side is slightly negative, right? And so what's this side? A little bit slightly positive. And so because of that, this molecule is polar. There is pulling. So let's just review these two in comparison. Linear and linear, but linear with same atoms tends to be nonpolar versus linear with opposite atoms or different atoms will be polar, okay? All right. Now let's take a look at another example. Let's take a look at some different shapes. In this example here, I have trigonal planar as a shape. They're both symmetrical. Remember, symmetry is that the outside atoms are evenly distributed. And so I notice that I have them all equally distanced apart. And in this example, they are the same. And this one also, they're very symmetrical, but, and that's a really big difference right here. One of the atoms is chlorine. So this symmetry is definitely thrown off. And so I look over here and I say, okay, I know fluorine is very electronegative. It has an electronegativity of 4.5. So my dipole moments are all pointing towards fluorine. I already drew that one, but I'll draw it again. And this one, my dipole moments drawn towards fluorine. But in this instance, right, my dipole moment is drawn towards chlorine, but the difference is not as much. So look how small I draw that dipole moment. Okay, the difference between this and this is 1. The difference between this and this is 2. This is twice as much pulling. So these dipole moments are definitely much bigger, right? Which means this side over here is going to be slightly more negative versus this side over here, which is going to be slightly positive. That unequal pulling makes this one right here polar, giving it poles, versus this is being non-polar, evenly distributed. Okay, let's take a look at some other examples of shapes. So here is trigonal pyramidal versus planar. And in trigonal pyramidal, if you've noticed, I've written that it's asymmetrical versus trigonal planar, which is symmetrical. So in this example, I definitely have all the same atoms, right? Green little spheres. There's no lone pairs on the center. And now let's look at lone pairs on the center. So if my lone pairs are on the center, that means that I'm going to have pulling happening closer up to the top atom where there's the lone pairs versus here evenly distributed, right? So this is symmetrical. My atoms are evenly distributed around, and this one's asymmetrical. I have them all over on this side and no atoms over here, asymmetrical. So this one's going to be polar, and this one's going to be non-polar. No pulling, because it's evenly distributed, no pulling of electrons, versus polar. So this lone pair up here gives this side a slightly more negative, and this side a slightly more positive, making poles. Lone pairs are one of the things that we had talked about earlier to look for. Lone pairs will automatically make your molecule asymmetrical. So if your molecule has a lone pair on the center, you're going to be polar. So trigonal pyramidal will be polar. Okay. Let's take a look at tetrahedral. Okay. So in this instance, tetrahedral, what's the only difference? Different atom bonded to the center, all the same atoms. All the same atoms bonded to the center. And remember, it's easier to look at this if we have a real molecule, which I'm going to go get. So the symmetry is kind of obvious when we look at the three-dimensional. It's the same, it's the same, it's the same, it's the same, no matter how many times I try to spin it. A little hard to see on my paper here, but in 3D, it's much easier to say that this is definitely symmetrical no matter how I spin it. Well, if I change out this atom for a different color, then it's no longer symmetrical. So asymmetrical when I have a different atom. Remember, the minute you become asymmetrical, you're polar versus non-polar. Okay, here are some good summary points. Polar characteristics versus non-polar characteristics. Let you take a second and look at those, right? Molecules with positive and negative ends, asymmetrical shape, lone pairs on the center, and sometimes the bonds are polar. Molecules without dipoles, and they're symmetrical. Another quick reference, and this is like a great cheat sheet, is nonpolar molecules usually are elements that are bonded to the cell themselves, so diatomic molecules, and hydrocarbons. But the hydrocarbons have to be regular basic hydrocarbons that only have carbon and hydrogens in them, so seen here. No extra elements like oxygen or chlorine. All right, to summarize, this flowchart actually might help you. The first thing you want to ask yourself, are any of the bonds, that's supposed to say bonds, are any of the bonds polar in your molecule, right? So again, you go back and you look at the entire molecule and you look at the bond and say, are any of the bonds polar? If the answer is yes, then ask yourself, is it symmetrical? If the answer is no, then the molecule is polar. If the answer is yes, it's symmetrical, then ask yourself, are all the outside atoms the same? If the answer is yes, then you've got nonpolar. If it's no, then it's polar. If from the get-go you ask, are any of the bonds polar? If the answer is no, then you're automatically not polar. So hence nonpolar. You have to have at least a polar bond to come over on this end and see what then you become.